Okay, welcome back, everybody. This session is devoted to discussing the hackathon. And I wanted to first give the opportunity for the people who were interested in participating but weren't able to present Tuesday to be able to present their material. We still have some people, we still have a number of people who are unsure about whether they want to participate. And we have at least 7 people, actually 13 people who are potentially looking to present their ideas. And so if you have your slide queued up, that's fine. If you don't, speak up when we get to you and tell us what you're thinking about, okay? So I need to remind you again that this is being recorded and live streamed. So please be aware of that. And I wanted to, actually, we'll flip the order. We'll do the additional talks first. And then we'll walk through. What I'd like to do is walk through the peoples who presented on Tuesday and give them an opportunity to say whether they've made any progress, what they're looking for, and anything else that we could do. We could create some additional breakout rooms if people would like to have a breakout room to chat with possible collaborators and this kind of thing. Please let me know. We can try to set that up for you. Put it in the chat. And when we're done with our discussion, we will have Josh take over and continue the presentation of the antimony models, and hopefully answer some of the questions that were being asked at the end of the last module. My only concern is that I do not see Josh on the call. I hope he is not having internet problems. He's coming to us from Puerto Rico, and so I hope that he's not having internet problems. If he is, we will improvise. So, reminder, we have the folder. Giuliano, if you could repost for me the Hackathon single slides folder for uploading your ideas. You're welcome to make those slide decks more detailed as you develop your hackathon ideas. We also have that hackathon ideas partnering document, which people have been using. And there is the hackathon Slack channel. So if Giuliano, if you could repost those links, that would be helpful, or I can do it as well. Okay, let me do it. So I think Giuliano may be trying to debug this issue with, okay. That was the slide deck posting. This is the Google Doc, and let's see where did the Hackathon channel go? So that should be all the links that you need for the moment. So I'd like to do the additional lightning talks. I think one person who was going to do this was interested in doing this just texted me and said they're not able to do it. Let me see if the people who did ask to do it are there. I see at least one of them is there. So why don't we start out with David? If you're there, why don't you tell us a little bit about your idea and make a little pitch if you'd like to have some collaborators.
Thank you very much. My name is David Fagbemi, and I will be discussing my project. So what I'm trying to do is I'm trying to model a cellular signaling pathway of human bronchial epithelial cells. So epithelial cells are the cells that line the inner coating of the bronchial of our bronchial system in the lower part of the lungs. It's what protects against respiratory viruses and other, external actors. So that includes things like allergens or smoke or whatever it is. So since all these foreign objects create a certain immunological response, like the release of cytokines and chemokines, we're trying to figure out how to predict cellular signaling response based on each and every one of those viruses. So we came up. What I'm using right now is a basic, a logic-based model, which is kind of like our base, which you kind of create a basal or a fundamental baseline model that will be able to show us, okay, how this is what happens when this virus comes into the system, and how we're going to be able to sort of, understand the pathway signaling system, because that's the most important thing we're trying to figure out, like how to understand the signaling pathway systems so that we can be able to, better design drugs to be able to affect each signaling pathway. What we use right now is NetFlux, which is kind of like an open source software based on MATLAB. It allows us to model these pathways. So I was trying to find out if there's any other tools that we can use in terms of in a spatial temporal context. For example, something like CC3D, which we mostly focus on which focuses mostly on spatial modeling. So I'm trying to find out if there's any other methods or models that we can use to be able to pretty much model this pathway.
Yeah. Okay, that's great. We definitely can come back to that. There are some tools. The problem with, I don't know NetFlux.
Yes.
The problem with writing MATLAB code is that it's not shareable, and it's not usually convertible. But there are some software tools that may allow you to convert, depending on how elaborate your models are. Recoding them in antimony may or may not be practical. If you have 50 equations, recoding them in antimony takes an afternoon. If you have 2,000 equations, recoding them in antimony takes a long time. But in principle, these kinds of models can be expressed using the language that we just showed today. If there's an exporter from NetFlux to SBML, then the models can be read and written directly in CompuCell. And if it's all exported to SBML, it can also be turned into antimony if you want to be able to edit it. So those are things that can be explored. Okay. But that sounds like a great project. So we can definitely talk more about that.
Can I show you like an example? Can I share screen and show you an example of a signaling pathway just to give you an understanding of?
Sure.
Okay, sure. Here. Give me a second. Yeah, so this is an example of a signaling pathway here. Let me zoom it right in. So you have the receptor levels. So there's multiple stimuli. There's multiple stimuli that can be used, and we can see each. Let me shrink this. Okay. So previously, what has been used to model a system like this is we mostly be focused on gene expression, but we realize that gene expression is like the final phase of a cell signaling pathway. So we're trying to go through the entire cell signaling pathways to sort of understand, we're trying to understand, okay, the entire network. And if we can understand the entire network, we can be able to predict cellular response. So that's pretty much what we've focused on. So here you can see our stimulus, our input level, which is the stimulus level. Then we see the receptors. Then we have the adapter molecules. all the way down to the release of our cytokines down here. Hold on, give me a second.
And is this a Boolean model then? Is
Yes,
this a
so
Boolean stochastic model?
Yes, so we use a mixture of an ODE and a Boolean model. So we call it a Boolean-based or a logic-based differential equation model. So we try to combine both of them because both of them, as good as they are, they both have their strengths and their weaknesses. Boolean models are more scalable for a large network like this, but it doesn't give us the specific, it doesn't give us a lot of mechanistic insight or quantitative. In terms of accuracy, that's what ODEs do. But ODEs cannot really be applied to like a very massive like network like this. I mean, we can use them, but it's so cumbersome. So that's why we try to combine both of them. We use the scalability of a Boolean model and we use an ODE to give us much more accurate, understanding of the dynamics of this cellular signaling pathway.
Okay, that's so CompuCell now supports Boolean models through MabBoss. So if we could translate your code here into MabBoss, then it can run. And the ODE models are supported through SBML, CellML, or antimony. So in principle, we could do this. Of course, the amount of effort to translate, it will depend on, we'll have to look at it, but it's definitely a reasonable thing to think about. That's a great project.
Thank you, sir.
And seeing that in a spatial context would be fascinating. So let's go on through the other talks, and then we'll come back, circle back, and let people discuss more. So that's great. Thank you.
Thank you, sir.
The next talk was from Hamed. Is Hamed here? Let me look at our participant list, see if they're here. Okay, I do not see Hamed here now, so we'll go on. The next talk was from Marco Rusconi. Are you here?
Yes. Can you hear me?
Sure, please.
Okay. So thank you very much, first of all. This is an amazing workshop. And my name is Marco Rusconi, and I'm a PhD student at Institute Curie. For the hackathon, I'm proposing this 3D model of cancer invasion, which include an intracellular signal, intracellular signaling, this Boolean network. I already developed this model with PhysiBoss, which comes from the merge of PhysiCell and MabBoss. And so the objective of this model would be to simulate the different modes of cancer cell invasion through the extracellular matrix. So to monitor single invasion, collective migration, and trail migration, while also considering the formation of invadopodia or lamellipodia. So the goal would be the goal of this model would be to actually introduce some mutation in the Boolean network and see the actual results on the simulation. Like for example, what I did with PhysiBoss was to mutate one of the node of the Boolean network with MabBoss and completely block or force migration in the simulation in order to reproduce an in vitro experiment from Lodilinski et al. And also in the future, I would like to, since this Boolean model is still a work in progress, I would like to, in the future, to include new pathways to also reproduce these experiments where lamellipodia are activated through stimulation with blue light that activate OpSCC. So that's it basically. And I already developed this model, and I have here, if I can show the screen, I would like to show a 3D example of the model. Here, I don't know if you can see it. So I would like to reproduce something like this with Compusel 3D. The white cubes are basically extracellular matrix, and so the cells would degrade and escape through the extracellular matrix, and the microenvironment would be composed by extracellular matrix, TGF beta, and oxygen, and those would be also the input of the Boolean network.
Right. Well, that, I mean, the only thing, how many cells are in that simulation?
So in this simulation, I started with, if I remember correctly, something like 500 cells, but maybe this is a bit too much.
No, that's fine. For 500 cells, it's no problem. So I don't know if you were on yesterday because of I know the time zones are a problem for Europe. But when Josh showed this, the simulation, the chemotaxis simulation, where the cell consumes ECM and then migrates in response to the gradient it creates.
Yeah,
that's essentially exactly this simulation.
Yeah, exactly. In fact, I was super interested in
that. And now that we have the MabBus integration, assuming it works, because I haven't used MabBus, so we need TJ to do that. But in principle, converting this model over, there always are problems. My instinct is it's a 2-hour job to convert it.
Mm-hmm.
In practice, it's probably 2 days.
Okay.
Because there are always bugs. But doing this conversion should be straightforward. If the MabBus model works, it's fine. The cell ECM interaction is fine. I don't see any problem. That's a great problem. I would love to see that implemented. So I hope some people will decide to join you. If not, we'll be there to do our best to support you in that. So that's great. Thank you very much.
Thanks to you. Thanks to you.
Okay. And then the next one, Suvik here.
Yeah. So, okay. So let me share my slide.
Okay. Well, I should have. So do I not have the?
It's saying that you cannot start screen share. Okay.
Was this a movie or is it a static image?
It's a static image, yes.
Okay, so tell us what your idea is.
Okay. So before coming to this work, so I don't have much idea about the Compusel 3D, but so I have learned a lot from this workshop, and thanks to organizer and also the participant for this help. And so I will be studying a very simple model. So it's basically I want to study the confluent cell monolayer with cell division and apoptosis, and I want to characterize the glassy dynamics within this type of model. So the motivation behind this work is basically the collective motion of cell in a confluent monolayer is important in morphogenesis, cancer metastasis, wound healing, and etc. So recent studies and experiments have shown that the dynamics in such cellular system has remarkable similarities with that of a glassy system. So by the word glassy dynamics, it refers to the extreme slowing down of the order of like 10 to 12 order of magnitude with a small change in control parameter. And so that glass transition occur without any reasonable signature or reasonable change in the structure or any phase transition. So in this project, I will be in the context of the active matter. What I will do, so I'm interested to see whether this glass transition can be found in the cellular POTS model using Compusel 3D, and in presence of this cell division and apoptosis, which is the cell cycle events. And I will also like to study how the rates of the cell division and apoptosis affect the glass transition. And also, if time permits, I will also like to study the active polar cell to characterize the glassiness in this type of polar cellular model. So, and also I'll also like to see that if there is any lattice type effects or not. I hope that there will be no, but that I will like to check. So, and that's the plan of my study in this hackathon project. Thank you.
Okay. I realized that what was covered yesterday by Gilberto went by a little fast for some people, and I definitely, but Gilberto's done a lot of work on the statistics of tracking cells. And so I think a lot of the how determining the trajectory of the cell, calculating mean squared displacements, these things are things that he's an expert in. So if we could get him involved.
So I have a short discussion with him in the Zoom chat box. So that helps a lot actually.
Right, great. So that's
and also Professor James Lucas helped me in some.
Good. Well, I think you're joining in the middle of the night, so I appreciate your staying up at night to be part of this.
Thank you.
Okay, great. Okay, so those were our new presentations. So now I'd like to run through the list of presentations that were already made and give people the opportunity to update people. If you don't want to update, that's fine. Just say that you don't have anything to say, or if you're not here, of course. I guess what's the Yogi Berra comment that if people don't want to go to the ball game, nobody can stop them. So if they're not here, it's going to be hard for them to speak. So, but if you'd like to do an update, we can do that. If you would like us to create a breakout room so you could have discussions with team members, that's fine. Please let us know, post in the chat, and we'll do that for you. The one problem that we have with Zoom when it's set up the way it is that I cannot leave the main session. So the person who owns the Zoom session has to stay in the main session. And so I am restricted. I'm happy to talk to people one-on-one, but I'm restricted to staying in the highest level of the Zoom. I can't join the breakout room. But if people would like to have a breakout room, that would be fine. So I'll just run through these, and if people see their names up on the screen and they're here and you'd like to update us, please let us know. If I don't hear from you, I will go on to the next one in just a second.
Professor, can I share my screen?
Please, go ahead.
Do you have my screen?
Yeah, that sounds
Yes.
Yeah, the project was about the mechanobiology of endothelial to mesenchymal transformation for the calcific aortic valve disease. In this project, we possibly try to apply some shear force on the endothelial cells and some maybe chemicals or cytokine or whatever. And in order to see how the endothelial cells can now trigger to secrete some chemicals in order to degrade ECM and go inside the ECM and make this transition. So just as preliminary test with the computer cell, I made some modeling, but it is not, I was just playing with the things that we have learned up to now. So here, the red cells are the endothelial cells that I put. The yellow one is the base membrane layer, and the green ones I modeled as the ECM. What I did here, I put some cells like the blue ones in order to secrete. And once the secretion of some chemical field reaches to the endothelial cells, then they triggered and they start secrete another chemical in order to degrade the ECM, and using chemotaxis, they try to dig into the ECM.
So that actually sounds a little bit like the proposal that we just heard for the cancer model from Marco, right? With the degradation.
Yeah, here I use the adhesion flux for the energy. I mean, I defined some cadherins and integrins, but I need to adjust the parameters for them because for the chemotaxis, they build up on top of each other. I mean, the red cells. And we go like this. So I was thinking to divide the cells, endothelial cells, for different types, and when they are activated, I apply chemotaxis on the activated ones to not get other cells involved in the chemotaxis. So I am trying to figure out how to apply chemical force on top of these endothelial cells. And also, this would be kind of multi-scale modeling. So for the endothelial cells, I'm trying to build with the tellurium subcellular model. That's it.
Well, that's really impressive. One thing that sometimes happens with chemotaxis is that to get the chemotaxis forces to work properly, in a lot of systems there's adaptation, and in that situation, it's easier. What you could do is you can adjust the strength of the chemotaxis parameter cell by cell in response to the level of the concentration. So you essentially make it a logarithmic chemotaxis. That should really be a built-in function in CompuCell, but you have to do it by hand. But you scan the cell, you find the mean value of the chemical field for the cell, and you divide your chemotaxis parameter by that. That allows to have a much stronger chemotaxis response. But this is impressive. I hope it will inspire. I hope that will inspire people. I think it's a great.
Thank you. And also, I'm thinking that, for example, when the cells, the endothelial cells are activated and they secrete some chemicals, then other cells follow them because of that secretion. But I end up seeing that they are kind of bind them together and go another way, like fly. So other ways because of their mutual interactions that trigger each other.
Yeah. So that's something we can. Yeah, the chemotaxis is complex. You get there are a lot of, because cells respond very differently. Some cells only measure the chemical concentration at their leading edge. Some respond in different ways, and so there are a lot of options to consider. Again. One of the things that we did get to, it was already complicated enough yesterday, was the model Gilberto showed. You could bias that with chemotaxis and then have those cells crawl up a chemical gradient. So there's a lot to do. That's really impressive.
Thank you.
So I hope are you looking for people to work with you, or do you want to just do you want to do this on your own?
Actually, 3 people told me to join with Dr. Tion West, I think, one, the Narshin Fatima, they are not here, I think, and also Noah Ishkar. So if somebody else want to join, it would be appreciated.
Okay, great. I will create a breakout room for you just in case. The one problem with the breakout rooms is I have to create them all at once. I can't add a breakout room while they're open. So I apologize if I have to wait a second for doing that. But that's wonderful. That's impressive. Let me go back to the screen share. Okay, the next talk I was AJ, and did you have anything to update? Comments?
I don't have an update really. I guess my plan was to work with Abhishek, who's a postdoc in my lab.
Right.
And I haven't heard from anybody, but I'm okay with working with Abhishek. But I would, if somebody wants to join in, they're welcome.
Okay. So I guess the one problem with the I'll put the list of projects back on the screen at the end, because if people want to join breakout rooms and they're named after the speaker rather than the topic, you have to remember who's doing what. Okay, great. Farnoosh, do you have an update?
Can you hear me? Hi. Yes, I have something to say. The title of our project, as you see here, is Modeling the Immune Response Following Monogenic Cell Death in PDAC. I was lucky to have 3 teammates so far. Madish, Tahrim, and Paula have joined, and now we are a diverse team with teammates from all around the world, and with diverse expertise, with biology background, modeling experience, and Python skills. But we are all beginners in CC3D, and as we have still 1 or 2 places on the board, we would be happy to have a 1 or 2 new teammates, especially with CC3D experience. Today, we had a meeting together, and it was very great experience, and I think you have fun during the hackathon. I already talked with TJ, and he had some piece of advices. He also told that probably Joshua can help us, and Joshua kind of accepted to have a meeting with us probably today after the workshop or tomorrow before the workshop.
Wonderful. I'm really pleased to see people getting things organized. I'll create a breakout room for you. Again, these aren't, the Zooms are not the most efficient way of doing these kinds of organization, but at least we have some. Okay. Sorry, go ahead. Were you not, did you have something else you wanted to say, Farnoosh?
I don't know if it is possible for Joshua to have a breakout room now. I don't know, because he was busy today. So
He's here.
Yeah, I'm available.
Okay. So the only thing is the only problem is I can't create the breakout rooms. I can't add to the breakout rooms while they're open. That's the only problem. So give me, let's spend just a few more minutes going through the list, and then I'll open all the breakout rooms and people can organize, okay? If that's all right. I don't think it should take too long. Megan, you have an update. I know you said you have a good team put together.
Yeah, can I share my screen? Okay, can everyone see my screen? Great. So just a quick update. I have a proposed team. So me, Tian, Alexa, and Aaron, but we're still open for anyone else who's interested in joining. We've kind of fine-tuned our goal a little bit. So we want to develop an agent-based model of skeletal muscle that predicts the dynamic regenerative response of muscle cells, fibroblasts, satellite stem cells, inflammatory cells as a result of an acute injury, and also potentially look at varying levels of estrogen. So our specific modeling questions include: how does estrogen alter the outcomes of muscle regeneration? Do spatial inflammatory cells and growth factors change the injury recovery dynamics? Comparing that to a previous model that we have that does not have spatial aspects for the inflammatory cells and growth factors. And also looking at the initial conditions and which of those have a major influence on muscle recovery. And then at the bottom, I included a screenshot of kind of what we would envision the model to maybe look like. So importing some type of muscle histology, and then you would see the damage and the cells move around and help regenerate the muscle fiber.
Wonderful, thank you. So, Yajun, is it?
Hi, I have nothing to update. but I'm still welcome if anyone is interested in this neurons migration modeling, and it's also okay if I just do it by myself.
Okay. All right. Aaron, are you working with Megan? Is that right?
Hi, yes, I am going to be working with Megan. I did also get a message from Kato. Sorry if I'm mispronouncing that, but I didn't hear back from her. So I don't know if she wants to work on something on this in general, but I can hear from her independently if that works.
I just want to make sure that if people want to I'm sorry again, this is always a little bit klutzy with the all right. Janos or Janos?
Yeah, I'm here, thank you. I updated the slide deck with one slide about my previous ideas. Which
so you want to show a new slide?
Yeah, I can share my screen. Maybe. Okay. How do you?
It's starting.
It's starting. Okay. Do you see my screen right now?
Not yet.
Not yet. Okay, it's it's a bit slow. Okay, so what's the problem? Okay, is it visible or not?
Maybe no. Let me take the screen share back and
okay, and I updated at the slide deck these new slides, so you can also show it if it's easier that way.
Let me see if I can find it. Give me 1 second here. There it is. Okay, does that work?
For me, it's still frozen somehow, the screen.
Okay, for some reason. All right, is that working for people or not? Okay, can you try to stop screen sharing?
Actually, I can see the PowerPoint on my phone, but I can see it on my laptop. I don't know why.
All right. I'm sorry. Maybe,
okay, now I see it.
Okay. Okay. Go ahead.
Okay, now I see. Yes. Is the new information on the second slide that I thought that the tumor model from yesterday, it's a bit similar to what I'm trying to do. It's on the second slide because it has two cells, one that divides at the edge because it has nutrient and so on, and at the center there are cells that not divide anymore because they don't have enough nutrient or oxygen or something like that. So, but it's a three-dimensional colony, so some kind of gravity and this gravity would be needed, and also attachment between cells. I don't know which is the easier, making a three-dimensional model at first, or a two-dimensional slice, like in the images, in the microscopic images? What is the easier to implement in the system?
Well, I guarantee a 2D
one of my
model is easier to start with. The 3D models sometimes the 3D is essential. So when you need 3D, you should do 3D. But they're bigger models, they run slower, and they're a little more complicated. So I would start with 2D. Julio will show a buckling model, epithelial buckling model tomorrow. And if you combine that epithelial buckling model with diffusion limited growth, I think you could probably replicate this pretty well.
Okay, then it's great. It's great. I already talked about with Tahrin, but I'm open to have other group members to work with, because I'm new in CCD. I already did modeling in MATLAB, but it's the computing language is quite different. But these images show how the model should look like. Yes, how the result should look like qualitatively. So I would like to get something similar to that.
I think that's quite reasonable. So I've created a breakout room. Again, I apologize to everybody. I can't create the breakout rooms until we're done with this section, because I have to do them all at once. So let's quickly go through the list of updates and people who would like the breakout rooms, and then we will together. Great. Okay, is Kafyan Atari?
Yeah. Hello all. Well, actually, I don't have much of an update, but Giuliano agreed to give me a hand during the hackathon days. So again, if someone is still interested in this project, I am open. So that's all.
Okay. All right. Maria? Maria here? No. Okay. Lorenzo, thank you for all your help.
No worries. Well, I don't have big updates. In general, the project is still on looking at Notch and trying to extract some information and modeling that from data and modeling that. And essentially, I think the task will be implementing proliferation in a pre-existing base of model, and perhaps the most interesting bit is trying to set up a parameter scan and try to see how we can convert the data back and cross-analyze them with our experimental data. So I'm happy to have anybody on board. If anybody wants to or is interested, I'm open.
Okay, so I'll create a breakout room for you. So is there anybody who has not spoken so far, who is interested in proposing a topic?
Hi, yeah, I have a project I'd like to propose, if that's okay.
Okay, I'm sorry, can you introduce yourself? You
yeah,
need to screen share.
I'm Jonas. I did upload it in the Google Drive, but it was kind of just a few hours before the course, so I can just share my screen if that's easier.
Okay, sure.
Let's see. All right, can you see this? Can you guys see this? Oh, sorry. Yeah, so the project that I'm going to try and do is to model the effect of mitotic count and tumor-infiltrating lymphocytes on the radiosensitivity of HPV-associated oropharyngeal squamous cell carcinomas. So just a bit of introduction about it. These human papillomavirus OpSCCs, they tend to have a pretty good prognosis and respond quite well to radiotherapy. And also another thing is that these patients with high numbers of lymphocytes in the tumor immune microenvironment, they also tend to have good outcomes.
At some point,
And
I
one
should
thing
get
that
my mum.
one thing
you
that
have
we
to be there by 2:30.
Yeah, I have a 1:30 call, so
hello.
Ajay needs to mute. Yes, thanks.
So should I continue?
Yes, of course.
Oh, yeah. Okay, sorry. Yeah, so I was saying the one thing we also know is that high mitotic rates of this tumor cell is one of the reasons that has been suggested for its radiosensitivity. But of course, with a lot of other tumors, we know that if a tumor has a lot of mitotic counts, they tend to be quite aggressive and have poor prognosis. But I think in this case, the pathologists are not very sure as to whether or not high mitotic rates are a good or bad thing in these tumors. So what we have is actually H&E biopsies that we have processed through an image analysis workflow, and you can see that we have the outputs are the single cell maps of the tumor cells, as well as the lymphocytes, which are here. We also do have information about which cells are undergoing mitosis at this sort of snapshot in time, and also which cells, which lymphocytes have infiltrated into the tumor islands. And so the idea that I'm going to try and propose is to develop really two basic models. One is to model the effect of mitotic count versus the aggressiveness of the tumor and the radiosensitivity of the tumor. And the other would be to try and model the infiltration of lymphocytes from the stroma into the tumor islands in a sort of chemoattractant or chemorepulsant type of situation. Yep, and I'm really happy to have anyone, if anyone's interested in this project. That's all. Thanks very much.
So I think that's everybody. Appreciate your so I think I have everybody's down as a breakout room. I will open the breakout rooms, and people are free to join and go in as you see fit. Please let me know if you have any problems. I've tried to give the breakout rooms names that are at least partly descriptive of what people describe. Everyone should feel free to join in. If people want to talk to me, as I say, I need to stay up at the top level just because of the way this is structured. We have breakout rooms for Megan Haas on skeletal muscle, Ajay on lateral line, Javid on tissue invasion, Farnoosh on immune response, Ayajun on neuron migration, Aaron on zebrafish epibole, Janos on East colonies, Imam on cartilage, Lorenzo on delta notch, Jonas on mitosis and radiation, David on bronchial signaling, Marco on cancer invasion, and Suvik on cancer, and Suvik on Glazier epithelia. And for those of you who are not interested in joining a team, we can chat, or you can take a coffee break, and we'll let people have a conversation. Again, I appreciate people's patience with the running a Zoom meeting this one. But I think they're wonderful topics. I'm really pleased that and some years the topics that have been proposed are not good matches to CompuCell. I think every one of the topics that's been proposed is achievable. Whether we can achieve it in 2 days is another question, but achievable. And I do appreciate people's patience for this bug in 4.2.5 with tellurium. So feel free to unmute and speak up on any topics that you find useful. This is just a list of the speakers from previous. If anybody needs help moving into a breakout room, you should be able to move on your own, but if you want to move into a breakout room and you can't do it, put it in the chat and we'll go from there. Well, the next session depends a little bit. The next section will start at, let's see, in principle, it should be 2:15, is that right? Gosh. And again, free to have a conversation now while we're discussing. TJ, are you there?
Yes, I'm here.
So there's a problem. Antimony tellurium doesn't seem to work in 4.2.5 in the Windows install for some people.
Really?
Really. It works in mine, but it throws an error. So if anybody who has had this trouble this morning and that would like to explain the error, that would be a good opportunity.
I think that in the latest hotfix, antimony got kicked out of the binary installer for some reason.
So is that just a problem on NanoHub?
Windows.
NanoHub works.
Yep.
And again, people are free. I just wanted to let the TJ know about this issue. Somebody just put this. Okay. Thank you for sharing the error message, Joseph.
A question of the hackathon.
Yes, please go ahead.
As an observer, I may be curious to go from one break room to the other.
Yes.
And not promising to contribute anything, but just out of interest. Is that possible?
Of course.
So
I mean, I suppose the team,
breakup rooms will be advertised then?
Well, the breakout rooms at the moment are just for this next half an hour.
I'm clear about that. I'm asking about Saturday, Sunday.
So for Saturday, Sunday, you're welcome to come. And I mean, I suppose if the team says they don't want an observer, they can say that. But the plan is that I'm sure that people would be happy to have somebody to discuss with, even if you're not a main participant. But the organization.
There will be a list of breakup rooms that I can move.
We'll do our best. Yes.
Yeah. Okay. Appreciate it. Thanks very much.
Okay, so concerning the bug, there is a way that I can walk Windows users through for fixing that. I don't know what that does for us, but it's a pretty simple fix. I don't know how this happened, but yeah, we can fix it with should be one command in the terminal.
If anybody wants to move to a breakout room and is having trouble, either speak up vocally or put it in the chat and I'll move you. So TJ, do you think that there's a fix we could send out to people so that when Josh starts his presentation, people can run?
Yes.
Okay.
I can write up the instructions to send out via email and post in the Slack, and then can walk people through it as well whenever necessary.
So, Iman, I sent you an invite to the breakout room. You should be able to join there, but yeah, okay, you're there. I see a lot of people who are alone in their breakout rooms. So I don't know how efficient this is. I mean, it may be that it might not be a bad idea for people for instructors to migrate and check out the breakout rooms if possible. If you have the fix, perhaps we should make that an announcement for the group.
Okay, I'll write up the instructions now.
I know things have been complicated today, so I appreciate it.
Yeah, no problem. Sorry this happened. Again, I'm not sure how this happened because this is not something that typically changes in our binaries.
Well, I was surprised because I was working yesterday. I mean, it works for me for the.
And James, have you installed the 4.2.5 binaries?
Yes.
And you have a Windows, but other people aren't getting it. That's.
But it seems to be the Mac and the Linux people didn't have a problem. And it works fine on NanoHub.
Okay. So I'll talk with Matt about that. That's, yeah, that's very peculiar.
Does anybody need to have be moved to a breakout room, want to discuss anything, or we have about 20 minutes now to have free discussion.
I actually, let's talk a little bit about the project that I'm working on. I'm not going to be there for the hackathon this weekend, so that's why I have been involved with that. But yeah, I could do that here or in a breakout room with someone. It's a very simple project in a sense that we're just trying to smush some cells to recreate some shapes that we're seeing. And in a way, it's kind of misusing CompuCell3D because they're not actually even cells that we're modeling. But CompuCell3D was something that allowed us to change the shape while retaining the volume very easily. But let's talk to them about how to get, because what we're doing is starting with spheres and then wanting them to deform by kind of smushing into each other and lying with each other. And so I did that initially by just trying to make some contact energy between the cells so that they like zip up together. And it somewhat works, but the problem is that they have too much of a tendency for the membranes to just kind of get all variegated to maximize that energy by interdigitating a bunch, which is not what we want at all. We really want the whole structure to kind of smush up against each other and eliminate any space between them. So I'm not sure if like some sort of force or gradient or something would be best, or.
Well, so with the cell models, typically what you do then is you constrain the. Did I lose my internet connection?
No, yeah.
Okay. Did you constrain the surface area of the cell separately from the contact area energy? And so if you want to use a negative contact energy for axial adhesion, then if you don't constrain the surface, the cell will create an infinite amount of contact energy and basically turn to dust.
Mhm.
But if you constrain the surface area separately, then you can define the surface to volume ratio of the domain of the object and have the adhesion do the things that you want. It tends to be a little finicky in terms of parameter choices. You have to fine tune it a little bit, but that does tend to work. But I don't know if you have a simulation you want to show quickly while we're discussing.
Sure. Or maybe what I can show you is some like screenshots. I'm trying to think. It runs slowly because it's a 3D simulation. Right. Yeah, let me just a moment and I'll see if I can grab some screenshots that I've saved. I don't know if Garrett is here. I have a student.
I'm here.
Yeah, if you have any screenshots, Garrett, just kind of like a final.
Oh, I have a ton of them.
Yeah, you do. That's what I was thinking. Then maybe you'd like to. Yeah, I mean, I'll let you do that, Garrett. If you could share a screenshot or two of what it.
TJ, I think Marco would like to talk to you about the Mambos project, but probably you should send him a message about that.
Okay. Do I?
Or if you want to join his breakout room, I think he's sitting there waiting for you.
Oh, yeah. Who did you say was again? I'm sorry.
Marco Ruscone he's a Mambos person.
Okay, so this is one of the ones we've been working on.
So again, these start as spheres, and then after 1,000 steps or whatever, 600 steps, it looks like, they did smush together, but they also, the boundary is getting all messed up.
So yes, so then depending on the physics of what you're trying to model, it may or may not be true that the surface area is constrained. If it is, then that should help.
Okay. No, I mean, of course, just smushing a sphere to anything that's not a sphere also increases the surface area, but I suppose less so than all this pixelation, so it should still help. Huh?
Right. Okay. So if you add a surface area constraint, that should help a lot. The one thing you have to do is if you're changing the target volumes, then you have to adjust the target surface to match.
Right.
So one thing that happens is typically when we grow cells in a tumor simulation or something like this, we adjust the target volume. Mm-hmm. And then you have to, but if you don't adjust the target surface area to match that, you'll get, it's like blowing air into a beach ball. It'll get stiff. Right. And so you have to then do usually a back of the envelope calculation where you say, if it were a sphere, how much surface area would I have? And then you adjust that, you calculate the effective radius and you adjust the two parameters together. So you change the volume, the surface area to be like the volume to the 2/3.
Yeah. We're not expecting to change the volume, so that should be okay. They should just stay with the volume they started.
That was actually a mistake that was made very long time ago, back in 1992, where the surface energies, we just, by default, the contact energies were defined to be positive on the assumption that if the energy differences were right, the actual value didn't matter. And in fact, things like the diffusion constants of cells actually are different. If you have a negative contact energy, you have a higher diffusion constant than a positive contact energy. Again, because of this fact that a non-existent unit of surface has an energy of 0. And so it's, in most physics, of course, only energy differences matter. Mm-hmm. And the only energies you've written down are the ones in your contact. But in fact, there's always a zero there, whether you've written it or not. And so going to between positive and negative contact energies actually does change the simulation, because you can destroy surface. And that's a trick that we run into a bit. Okay. Does anybody else want to join? Anybody else want to join a breakout discussion, or have any issues they want to discuss at all? We're a little more than halfway through the course, and I know not everything has worked, so I appreciate your patience with that. I appreciate you coming back despite that. So any comments or ideas that people want to bring up, please let us know.
Hello, Professor Glazier. I am Haplia Ioan from Romania. I would like to ask you something about not so technical, rather principle based. Would it be possible to change the relationship between the system being modeled, a biological system, and a model like CompuCell, to consider CompuCell itself as the object, the ideal object, and to replicate some parts of its behavior with simple ODEs. So we consider the spatial model as fixed and ready-made, and then try to find some parameters for an ODE that captures some parts of the system. Do you think it would be a fruitful direction or not?
So that's a fascinating question. Over the years, and I can't tell you how many years, it's 25 years maybe, Yanis Kavrakidis has repeatedly proposed that we should work on that problem. And somehow we never do it. So I think it's very interesting, because these kinds of spatial models are very expensive. They take a lot of computing. And sometimes the spatiality is critical and you need it. And there are other times when the result could be, for example, if all you care about is the volume of a tumor versus time, a population model may be sufficient to give you that information with a few ODEs. And so we mentioned briefly, but didn't really go into it. We just had a paper accepted on this that TJ has worked on, going the other way, where we start with ODE models and we turn them into spatial models, where we map the components, of the model very carefully, so that the parameter values in the ODE model are pulled in, and in the well-mixed case, give you identical results to the ODEs. And then you can ask the question, if there is spatial variation, for example, in a viral infection model, if not all the cells are exposed to the same level of virus, because there's diffusion of virus or diffusion of interferon, then the ODE model will not agree with the spatial model anymore. And in that case, you can ask, how are they different? And one of the things that you find out, for example, is that if you calculate the infectivity of the virus, which is that beta parameter that people use, if you assume an ODE model, which is a well-mixed model, then, and you actually do fit the curves for infection to the experimental data, you'll misestimate the infectivity because of the neglect of the spatiality. And so we've worked on the going from ODE to spatial models. Having formal ways to understand how to go backwards would be very, very helpful. And that's, I think, quite a profound question. The other thing people have thought about is whether you can use artificial intelligence methods to do what we would call surrogates, where you would, what you're proposing basically are ODE surrogates for particular whole models or components. For example, diffusion equation is very expensive to solve computationally. And so for big models, very often most of the computer cost is actually solving the diffusion equation. And so we've been doing some work trying to develop artificial intelligence. That's a fancy word. Neural network simulation. I don't like the word artificial intelligence, but people use it. Neural network simulations that say if you have a configuration of sources and sinks, what is the equilibrium chemical field? And if you can do that with a neural network, it runs about 1,000 times faster, even 10,000 times faster than actually doing the computation directly. And so the problem is the dimensionality of the problem is very high. So it's not an easy thing to do. But I think at least in principle, there's some very nice work that's been done. Heartflow Corporation, which does a lot of finite element modeling of tissue mechanics, has been able to substitute a lot of the detailed mechanical calculations with our AI surrogates. And there's a team at Yale trying to do diagnostics of aneurysms that's done some very nice work on AI surrogates. So those aren't quite the same. Of course, the neural network is more complicated than your ODE structure. But I think the idea of asking the question, can you reduce these complex models to simple underlying forms is very interesting. I know, what's his name? At Emory University has worked on this problem. Yanis Kevrakidis has worked on this problem, not using CompuCell though. I think it could be very interesting to do. I think it's a very profound question.
Oh, thank you. Yes, and yes, what this thing with space, like the brothelator and the whole idea about having different concentrations. Different concentrations. What if it was not alive? No, the species, chemical species would mix. So life appears to be somehow inherently spatial. Now, abstracting this away in an homogeneous model, it probably misses the very problem. No.
So what physiological models do is they don't represent space explicitly, but they do compartments. So you have a model of the gut would have many compartments, and then you pass material through that. And so effectively you're creating a surrogate, a one-dimensional surrogate of the space with ODEs. And so the most sophisticated commercial pharmacokinetic models have many compartments that when you swallow the pill, they'll model what happens in the front of the mouth, the back of the mouth, the throat, and each way down through the gut, down to the anus. They'll have, each of those will be broken down into a block with its own pH, its own temperature, its own exchange with the environment. And so you can always, I mean, in a sense, since space is always discretized in a computer, in a sense, you're running finite difference versions of ODEs, which are simulating PDEs. So in a trivial way, we're always converting space into ODEs. The question is, are there simple ways of doing that? And I think that's the really interesting question. In the same way, trivially, a neural network model, neural network, cellular automata. Cellular automata are universal computers. So you can solve any problem with cellular automata. It's just not very efficient or convenient. In the same way, reaction diffusion equations are universal computers. You can solve any problem using reaction diffusion equations. It's not very convenient. And so the question, I think, is that makes what you're asking profound is, when is there a simple ODE representation of the result? The fact that there is, at least if it's not a stochastic problem, is always going to be there. It's always possible. So there's an existence theorem there. but actually making it useful is not so easy. And I think seeing when there's simple regularities and problems is really an interesting question.
Thank you. Thank you. And now a more technical problem, using CompuCell as the command line. Is it supported? Is it advisable? Is it?
Well, if TJ is here, so again, the CompuCell, so CompuCell has always had, not always, but almost from the beginning had command line interfaces. And when we run large scale simulations on clusters, we run thousands of replicas remote. So so you can definitely call CompuCell with command line execution. Josh, maybe you can speak up on that.
Yeah. I mean, it's what you're saying is right. We can execute CompuCell from command line, and you can build sophisticated wrappers if you are familiar with it, so you can run parameter scans and so on using command line.
I mean, TJ and Josh have lots of Slurm scripts that will run thousands and thousands and thousands of jobs on a cluster. So
it works.
And TJ has been refactoring CompuCell also, so it's easier to call from Python. So traditionally, CompuCell has been good at calling other packages, but you've used CompuCell as the master package and then pulled the other packages inside of it. TJ has done a lot of refactoring, so you can do it both ways. So you can load CompuCell as components as a library in Python and then call it from other places.
Oh, that's great. I thought this was to be done some point in the future. It's already available.
I don't know if it's done. He's doing it, and you have to ask him how far along that project is. Maybe I'm old-fashioned because I grew up developing this code really as a desktop application in a time when everything was remote, and so I still tend to use it that way. But Josh and others will call it, and calling, for example, say a finite element package from CompuCell is possible. There's some nice solids modeling libraries or fluids modeling libraries, reaction diffusion solvers packages. If anything exists as a Python library, you can call it from CompuCell. Going the other way takes a little bit more work at the moment, but TJ has been working hard to make Python callable. And I'm pretty sure that most of it is now. Okay, we're actually almost out of time. I hope that those discussions, I understand that wasn't a perfect organization, but I hope that was useful. People had some good conversations. Was it helpful to have the time to talk a little bit? And if people were sitting in a room with nobody and waiting, I apologize. I figured if that happened for people for too long, they'd come back out and chat with the group. Let's see, Josh, we're supposed to end at 1:45, right?
Yes, and then next module
have a
start
lunch
at
break
2:15.
at 2:15.
Right.
So does anybody else have anything else to talk about? As I say, I don't get to talk so much because usually I'm running the meeting. So it's a pleasure to get to chat a bit with people. You don't have to be asking me questions. You can ask your other participants questions. You can. Josh is here I don't know, Josh, if you wanted to join. I see Yajun has been sitting on his own. Do you want to talk to him for a minute?
Yeah, of course. Yep.
Let's see, where are you? Oh, you have to, if I have to move it myself.
Yeah, I can join. I can join.
Okay, great. Okay. Any other comments? I hope it's not, again, I know this is a little chaotic, but the hackathon organization tends to be chaotic. But a lot of times interesting things come out of them. Last year we had some, we've been working with a team from NIH, from NIAID, on a project that grew out of the hackathon last year, on Leishmania infection. If there aren't any other questions or comments, I guess we can say we'll take a lunch break. I'll leave the discussion rooms open for the next half hour or so, and then we will reconvene at 2:15, and Josh will start showing you more details about how to use these subcellular models. Can I have a show of hands if you're on the call now? How many people are having this Microsoft, the Windows problem with running tellurium antimony? What fraction of people are having that problem? 1, 2. Okay, TJ said he thought he had a workaround. Did he talk to you about that? Okay, sure. And again, if I know it's not ideal, the two options that we have at the moment would be to roll back to the one version of CompuCell. So you could go to SourceForge and download the earlier version, which is not much fun, or to follow along today with NanoHub while TJ. I'm sure TJ can patch the source code between today and tomorrow, but I don't want people to miss the lectures this afternoon.